I should. Anyhow, here we are. We're recording now. So just to backtrack real quick, please pay attention to the dates above. We've been talking power series. And this important thing that comes along with power series is this thing called the interval of convergence. And why that's important is because power series can be treated like simpler objects, namely polynomials, when the interval of convergence is known. So let's get right into what we mean by that. You didn't finish writing that down? Oh my God, no, you're all right. I'm kidding, of course. You're supposed to. Yes, Eric, what's your question? Are you not paying attention? You mean time-wise or day-wise? I don't know yet. Do you want it early? I don't know. I didn't really think of a time yet. What time would you prefer? Lobby for it. Send me gifts. Please is a good story. Yeah. Oh yeah, I can do it. Sure. You want it 8 a.m.-ish? Sure. Maybe I'll even post it Monday night. What do you mean you have a physics test overlapping? What time is your physics test on Tuesday? 11. Yeah. I love when you guys complain you have multiple tests on the same day. Can you imagine if you needed surgery and the surgeon was like, nope, not today. I already did surgery this morning. Screw you. Yep.
My primary, we used to do like 6 exams just in one day.
Yeah. Well, that's that British education system. They don't have any, there's no ruthless. Yeah, but don't they model it after the British system?
Not really.
No, okay.
Separate. I did my high school at the British one, right? But before that, it's like you start in the morning at 6 till at night 6. Just continue.
That's brutal.
You have like 10 minutes break. That's it.
You guys want. See, if you guys spent time studying instead of worrying and instead of complaining, imagine where your brains would be. All right, anyhow, let's move on to this stuff. So here's the idea. Well, you don't suck. Stop saying that. Be positive, Emily. This stuff is hard, and I hope you mean 5 hours a day, not 5 hours the whole semester, which I'm sure you probably mean 5 hours the whole semester. Okay, here's an idea, or not an idea. Here's something to think about. So here's what we know. We know of one, well, at least one. I shouldn't say it that way. That's bad. So we know. So another way of saying what I wrote down on the previous page is the following. So if we know a power series converges, then it defines a function. On its interval of convergence. And so we already sort of alluded to this, but let's see what this gives us. So for example, we know this series, which is the geometric series. We know that the sum k goes from 0 to infinity of x to the power k, which is 1 plus x squared plus x cubed, etc. We know this creature converges for -1 less than x less than 1. In fact, we know more. We know that this thing actually, what it equals. we know that this thing equals 1 over 1 minus x. Okay, now we're not going to go through all this crazy stuff, but the theory of power series says that we can manipulate this thing using the normal algebraic and calculus sort of operations. So we can manipulate this equation to obtain more power series. So, for example, let me write down what we have again. Let's start with this formula. 1 over 1 minus x equals 1 plus x squared plus x cubed plus dot, 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 dot. So start with this. Now, replace x with, let's say, 2x. And so if we do that, we get 1 over 1 minus 2x equals 1 plus 2x plus 4x squared plus 8x cubed, etc. Now, there's no reason to believe that this is legal. There's no reason to believe that this formula even makes sense. We're going to show you that it does make sense, but let's play the game again. So let's go back. Let's give this a name. Let's call this star. So we're just going to manipulate the heck out of star. So instead of replacing x with 2x, let's do something else now. Let's replace x with minus 5x in star. So now I have 1 over 1 plus 5x, and that's 1 minus 5x plus 25x squared minus 125x cubed, and I get that. So again, I started with my geometric series, which we now know is a power series. And we know that the theory tells us that I can do this. What else can we do? Well, we can multiply by, say, x squared. So if I do that, I get x squared over 1 plus 5x is equal to 1. Well, this would be x squared times 1 minus 5x plus 25x squared minus 125x cubed. Or if you distribute that x squared through, you get x squared minus 5x cubed plus 25x to the fourth minus 125x to the fifth, etc. Now, I don't think I can emphasize this enough. The thing on the left is something that you first encountered in like an algebra class. It's a rational expression. The thing on the right looks like a polynomial, but it ain't. It's actually a power series because it goes on forever and ever and ever. So let's go investigate this for a second, graphically. Because there's nothing that should make you believe that something like this, which is finite, it's an expression. You plug in an x, you can compute what it is. There's nothing other than some heavy math that should convince you that whatever number you get over here should be the same thing that this series sums to. Let's go look at the graphs, though. So if I go to Desmos, and let's start with our function, which was y equals, what was it? X squared divided by 1 plus 5x. So this is our scary function. So I'm going to zoom in a little bit. So this is rational function. Notice it has an asymptote at -1/5. Now let's build our power series. What was our power series? Well, let's remember what it was. It was x squared, and then it was minus. What was it? It was minus. So the next term would have been, yeah, right. So it's going to be 5x cubed. So look already. What I want you to do, I'm going to zoom in. Look that the red and the black are right on top of each other. And then the next term was plus 25x to the fourth. And you'll see the red and the black are on top of each other. And then it was minus 125x to the fifth. And once again, the red and black. And what you're noticing is this red curve, as I keep increasing the powers, is doing what? Well, it's more and more becoming the black curve. Now, not everywhere. It's clearly not doing anything down here. But that shouldn't shock us. If I zoom out a little bit, and I say, okay, let's keep adding terms. What's the next term? Well, it's going to be plus, and then this is going to be the fourth root of 5, right? So I'll just do 5 to the fourth. And then this is x to the 6th power. And so now I'm getting better and better. And then it's going to be minus 5 to the 5th power. And then it's x to the 7th. So what's happening is over here, this is a really, really good approximation. Over here, it's not so great. It's up here. But I'm going to draw two lines. I'm going to draw x equals -1/5. And then I'm going to draw x equals 1/5. Say that again?
Use 1/4.
Yeah, this should be 5. So what's going to happen if I keep playing this game where I keep adding another term? My red curve is going to match the black curve between the blue and green lines. And the question is why? Well, let's see why. So before I leave this page, does anybody have a comment or observation or a question? Well, that's right. It's going to be because it only converges. This thing makes sense for all x. This series is not going to make sense for all x. It's only going to make sense for x in the radius of convergence. So this is what we have to understand. So if we go back here, the question we might want to know is, when is this valid? So we just saw that it's not true for every single value of x. So for which x is x squared over 1 plus, what was it, 5x? Yeah. For what x is this true? Well, we could look at the series on the right and determine the radius of convergence and the interval of convergence, but that we don't have to do that. That would sort of be like dropping an atomic bomb on an ant farm. It's unnecessary because we can figure it out from what we did before. So we know we can reason like this. Well, 1 over 1 minus x equals this. For negative 1 less than x less than 1. Thus, if we set x equal to, what did I do? I said negative 5x. So really what I'm doing is changing my variable, right? So let me not say set. That might be, well, actually it's not going to be bad. Let's say that again. Yeah, is that the word I used? Okay. So let me keep my same verbiage. So if we replace x with negative 5x, we get 1 over 1 plus 5x equals 1 minus 5x plus 25x squared minus 125x to the third power, etc. Now, where would this be true? Well, this would only be true if minus 5x is less than 1 or greater than negative 1. Now, this inequality right here is the same exact thing. If I solve it for x, is the same exact thing as x being less than 1/5 or greater than 1/5. And so that's how I was able to determine those lines. Yeah, right here. So the way I was able to determine those vertical lines were 1/5 is because I knew that when I plugged this in. Now, we know that this series converges on the right when x is between negative 1/5 and 1/5. Now, remember, the only thing that's going to matter when I go to my power series is going to be my coefficients. So when I multiply everything by x squared, I'm not changing the interval of convergence. Does anybody have a question about this? So what we did is we composed. I did a composition. I replaced one power series with, I did a composition, and that's legal. And then it's also legal to multiply by an expression. So what if I, instead of did algebraic manipulations to power series, that's legal. Algebraic manipulations are legal. What about calculus operations? So we can manipulate using calculus too. So let's start with it. Let's start with 1 over 1 minus x. If that's equal to 1 plus x squared plus x cubed, etc. And that's true when x is between -1 and 1. This means that if I differentiate this, they should be this also the same. So what's the derivative of the left-hand side? Turns out that you get 1 over 1 minus x quantity squared. And then the derivative on the right-hand side is just 1 plus 2x plus 3x squared. The next one would be plus 4x cubed, etc. So now I've gotten a power series for this.
So for you, when you're trying to figure out the series, right? You're using the formula we use, right? That if f of x, the first variable is equal to the one we studied, right?
I'm not sure what you're saying. What formula? You talking about Taylor series?
So how, one thing I don't get, how are you getting the pattern going on? Because,
How am I getting the pattern?
yeah.
Well, this pattern, this is the geometric series.
Yeah.
So what pattern are you not following? This is just x. This is x to the power 0 plus x to the power 1 plus x squared plus x cubed. So when I differentiate it, what's the derivative of 1? It's 0, so I get rid of it. What's the derivative of x? 1. What's the derivative of x squared? Well, the derivative of x squared is 2x. What's the derivative of x cubed? 3x squared. So I know the next one's x to the 4th, so that's 4x cubed. Does that make sense? Does anybody have a question about this? Take the derivative of this. This is, I'm just differentiating both sides. All right, instead of taking a derivative, let's now integrate. So if I start with this, which again has this pattern, and this is true for an x between -1 and 1. Well, this, by the theory of power series, we can integrate both sides of this. And so what I told you at the end of last class was that the theory tells us this is legal. So what's the integral of the left-hand side? The integral of the left-hand side is negative the log of 1 minus x. And the integral of the right-hand side is x plus 1/2 x squared plus 1/3 x cubed plus 1/4 x to the 4th, etc. And this is true at least between -1 and 1. So now we just found the power series for the log of 1 minus x. Now let's be careful what I reasoned here before anybody jumps ship. By the way, I guess I should be a little more careful because there is when we integrate, there's this arbitrary constant at the end. Does anybody have a question or comment about this?
Are there some times that you can start with the replacement and go to integrate?
Say that again?
For example, let's say the one we did, right? Where you replace x with 5x,
Mm-hmm.
and then you integrate that.
I could do that, yeah, absolutely. Mm-hmm. In fact, that's what you're going to have to do for your homework.
But how can you determine that? First, you have to replace, and after replacing, what is the step before going to integration?
Well, there's not going to be another step before integration, no.
So that's going to be replaced then.
It's, yeah, on the homework ones at least, yeah. But, I mean, you can go in any order you want. Now, it turns out a fascinating thing that this thing, and it's to prove it and to explain why is beyond the level of this class. But it turns out that this thing actually converges for -1. So the interval convergence actually will be including -1 here, not 1, but at -1. We'll get to that in a second. But right, and let's do one more before we sort of see what this leads us to. So let's do what you suggested. So you suggested, what if we sort of do a replacement, then either differentiate or integrate? So here we go. Let's do this one. Here's an important example. So I'll start with the same thing. Notice we got all this information just from this lowly geometric series, right? Of course, this is true for this. Now I'm going to replace x with x squared times -1. So this will become 1/1 plus x squared. So this is 1. Then this becomes -x squared plus x to the 4th minus x to the 6th, and then we go. And this turns out to be true between -1 and 1. You can do the algebra to convince yourself of that. Now, why did I do this? Well, what's the left-hand side look like? The left-hand side looks like the derivative of the arctangent. So if I integrate this, if I integrate both sides, I get that the arctan, or the inverse tangent, is equal to x minus 1/3 x cubed plus 1/5 x to the 5th minus 1/7 x to the 7th dot 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 plus c. And of course, this is true between -1 and 1.
So like the thing we get, right? The intervals we get for conversion. We just get it, but we're not sure if the last two.
That's correct. We get for free that everything between -1 and 1 it converges. but we have to do extra work to study the endpoints. And this one turns out that it will converge at x equals 1. But we can't. See, here's the thing. There's a difficulty here. It's a good question. Because if you look at this one, it turns out that if you replace x with 1, the right-hand side converges. But that doesn't necessarily mean that the number it converges to is the inverse tangent of 1. Do you understand? Turns out it will be, but we don't know that. Same thing on the previous page. If you replace x with -1, this will converge. Alternating series test is one way you can get it converged. That doesn't necessarily mean, though, that the natural log of 2, which this is the sum of this. It turns out it is, but there's nothing to guarantee. It's actually not easy to show that. And so in this class, we just say, hey, it's true. And we're going to get to that in a minute, but that's a good question. So there's two big sort of elephants in the room. It's the first elephant is, does this converge at the endpoints? And if it does converge at the endpoints, the question is the sum of the series the same thing as this number? We know for free, we get it between the endpoints. We get it for free between -1 and 1. We don't know what happens at the endpoints. And what we do know is outside of that region, nothing matches. So let's illustrate with this one. This is a good example. Let's go to our friend. We'll go to Desmos and graph it out. I guess I should hit the right button or it won't work. So let's look at the arctan, which Desmos knows very well. Looks like this, right? Now let's draw our series. What was our series? Our series was, well, the first term was 1, what, it becomes x, right? Right? And then what's the next one? Then it becomes minus. So it's going to be -1/3 x cubed. And right there, you see that we got a good match. So let's zoom in. Now we know it's going to be bad outside of, here's where we know it's going to be bad. We know it's going to be bad when we leave. Well, actually, here's a simpler way. Let's just look at this creature. Let's restrict where we're going to let x be. -1 less than x less than 1. That's the only place that the arctan matters. So but you'll see right there, it's a pretty good approximation. What's the next term? It's plus 1/5. X to the 5th. Now I'm pretty good again. And then it becomes -1/7. X to the 7th. And so you see that this is matching. Now it's not going to match anywhere else. It's only going to match between -1 and 1. But that's all the only place we expect it to.
So that's another big question, right? So when you go to the previous, so over there, right? So we started, our 1 is good, our power, it starts from 0, right? 0 to infinity, right?
Correct.
So 1. So when we integrate 1, we get x, right? So when we put x,
well, so are you asking how would I write this as a series?
yeah.
Well, you're going to have to re-index it.
So don't you use like 1? That's what I'm asking.
Well, you could start it at 1. Yeah. I mean, look at the pattern. It's not easy. So the question being asked is, how do I write this? How would I write this in sigma notation? I think is what you're asking. I think.
That's when we do this, right? When we're doing for the geometric series, right?
Yeah.
R has to be between -1 and 1, right? And the R is R power 1, right? R to the power of 1.
No, it's R to the power k, whatever the index is.
Yeah, so it's normally like starting from 1. You say
No. It's starting from 0 here. I'm starting from 0.
Okay.
Because this is the 0th power. This is the first power, the second.
You start from 0, right? But you said that when you're trying to determine if you use the first power, right?
I don't know what you mean by first power. I'm not sure what you're
R to
asking.
the power 1. When you're trying to find.
What do you mean R to the power 1? I don't know what you're asking. Why am I putting this here?
Yeah, so
Because I know that this series only converges when the number I'm raising to the index is between -1 and 1.
So for that number, it has to be to the raised to power 1. That's what I'm asking.
I don't, this number here,
No, x.
x?
Yeah.
I don't know what you mean. If you,
But
look,
x is the same as x raised to power 1, right?
yeah, but you're looking for a pattern that's not there. Look, here, let me explain. I think this is what you're saying, and I'm not positive. Let me get this out of the way. This thing, if you write this in sigma notation, this is equal to the sum, k goes from 0 to infinity of x to the power k. So what do you mean x to the power 1?
Can you just like continue? I'll just look for what I am.
Okay, that's fine. Yeah, you gotta let me know because I'm not quite sure what you're asking. All right, so okay, so the way to think about what we just did the last few examples on is that we can start with the geometric series, which we now know is a power series, if we think of the number as being a variable. And we can use that to determine new series. And so then the question you might have then is there a connection between this series? Because remember how we started talking about power series, we said that there's these thing called Taylor series, which were very natural. We got them by taking derivatives. So the question then might be, how are the above series related to respective Taylor series? So here's what I mean by that. So if I look at this, if I look at this last line on this page, I have a series for arctan. Is this, and we got this by manipulating power series. The question is this the Taylor series? And the answer is yes. And so the cool thing about power series is there's this uniqueness thing happening. So here's the cool fact. Power series have a uniqueness aspect. And so that is the Taylor series of the arctan must be the series we got on the previous page. So we're going to verify that, and then the rest you're just going to have to go on faith for the other functions. We're going to verify that that series we could have obtained in a completely different way. And then if we obtained it in a completely different way and studied its interval of convergence, we would see that we get the same thing. Does anybody have a question? Did you figure out your question yet, or your point? Shobit.
Yeah.
What was it? Bring it up to me. We have a question. Only those in class.
So for example, this, right?
Mm-hmm.
So R is this one here, which is R to the
No.
power.
R. What do you mean R is this one? No. This R, when we're doing this, R is a number.
Yeah.
We're just calling, could be any number. All we're saying is if that number R is between -1 and 1, this series converges. Now what we're saying with power series is don't say R is a fixed number. Let it be any number between -1 and 1. And since it can be any number, we're just calling it X.
So let's say R here like 4, right? So there'll
Yeah.
be 4 over here too. So you put 4 over here.
Right, but it wouldn't converge if R was 4 because it would be bigger than 1.
Oh yeah.
Yeah.
So you just use.
I'm using what, again, see, you're getting it confused. You're trying to look for patterns that aren't existing. You need to understand that this thing right here is we're saying, what this means is if this, whatever number is being raised to a power, if that number falls between here, we're good. So if we replace r with the standard variable x, then we're saying this only makes sense if x is between -1. That's all we're saying. It has nothing to do with this specific number. It has to do with what are we raising to the power.
So that will only continue till a certain place, right? Because for example, you say r is any number. So let's say if r is 1, right?
Yeah.
So
Well, it doesn't make sense because it would diverge. If r is 1, then you're adding 1 up infinitely many times. That doesn't make sense.
Okay, then let's say if you have 0, right? It's set at 0, so that's fine. And then it goes to 1. So it will only count for 0, right? It won't count for the 1.
I don't know what you mean by r. You're confusing what this means. You're completely confusing what this means. This means take a number and raise it to the kth power.
Yeah.
K changes at each step,
Yeah.
right? So if r is not between these two numbers, it doesn't matter.
Okay.
It doesn't matter. If r is 5, this makes no sense.
Okay.
If r is -10, it makes no sense. The only time it makes sense is if r is between -1 and 1. So if r is a half, it makes sense. You get 1 plus a half plus a fourth plus an eighth plus a 16th, etc.
Okay.
All right.
Yep.
Make sense?
Yeah.
All right. Yeah. So you're thinking about it in a way that is. So it's a good point you bring this up, because one of the things that we have happen is the lack of experience that you have at this level is that you're thinking. You need context. You need to understand that when we write the letter X, that can mean any number. Now, in that context, when I write something like this, if I go 2 pages back, when I write this, X can be any number. Context says K can't. K starts at 0, then the next time it's 1, then it's 2, then it's 3. So this right here, this means X can be any number on the planet. What we're telling you is the only time this equation makes sense, the only time it has meaning, is if X happens to be a number that's no less than -1 and no bigger than 1. So if X is 13, this makes no sense. If X is 29, this is meaningless. However, if X happens to be a half, this number, which turns out to be 2, is the sum of this series, which will be 2 as well. That's what we're saying. All right. And again, this is not easy to learn. It's like a mind. Every time you think you understand it, then 30 seconds later, you like take 2 steps back. That's how it is. I wish there was, I wish there was an easy answer I had for you guys. There's not many out there. All right. So anyhow, this will be good practice. What I want to do is I want to look at the Taylor series for arctan, centered at 0, and we're going to show that it happens to be this same series. And so what that tells us then is that tells us, because if you go back to the definition of Taylor series, we could write the Taylor series of a function. That doesn't mean it converges to the function. We think it does. The graph suggests it does, but we don't know that. However, if we can show that the Taylor series of arctan is the series on the right here, then we have no choice but to assume that the Taylor series actually is equal to the arctan, at least for values of X in between here. All right, so let's do that. So what is the Taylor series? Let us remind ourselves how to do this. So let's call f of X equal the arctan. And let's note that the first derivative is 1/1 plus x squared. Now, to make taking derivatives a little easier, I'm going to rewrite this. This is 1 plus x squared to the -1. So the second derivative is minus 1 plus x squared to the -2 times 2x, which we can write as minus 2x over 1 plus x squared to the second power. Let's do another one. One thing I'd point your attention to right away is notice, and this might not be a bad thing, notice what is, we come over here, what is f of 0? F of 0 is 0. What's f prime of 0? Happens to be 1. f double prime of 0 is 0. So we're already in a good place because notice, if you look at the arctan, notice it has no even powers. So all the even derivatives evaluated at 0 are going to turn out to be 0. So what's the next derivative? Now this thing is going to be a pain to compute, but we can absolutely do it. We're skilled enough. So it doesn't matter which piece you use. You can use this piece or you can use this piece. It doesn't matter. I'm going to use this one. So let's go real slow here. This becomes, I bring down the -2. I'm going to differentiate. I need the product rule and the chain rule. This is an ugly derivative. So I get +2, 1 plus x squared to the -3 times 2x, and then I have a times 2x. And then it's plus, leave the first piece alone, so it's minus this. So this is ugly. So it's minus the first piece times this second piece, which is just times 2. Ugly. But I don't care. Honestly, I don't care really right now it is. I could clean it up. But all I want to point out to you right now is that the third derivative evaluated at 0, what is it? Well, let's calculate it. If I plug 0 in here, I get 2 times 1 to the -3rd times 0 times 0, right? And then over here, I get minus 1 to the -2 times 2. So what does that equal to? Well, that, if I just, this goes away, so this is just what? -2, right? All right, great. So you could suffer through computing more derivatives if you wanted to. But I'm going to stop here. What I want to point you out to is the following. So let's build the Taylor series, at least the first 3-4 pieces of it. So here's what we have. So the Taylor series is, remember, it's the sum. You take the kth derivative evaluated at 0 over k factorial. K goes from 0 to infinity of x to the power k. So the first guy becomes just f evaluated at 0. Then it's plus the first derivative evaluated at 0 over 1 factorial times x, plus the second derivative evaluated at 0 over 2 factorial times x squared, plus the third derivative evaluated at 0 over 3 factorial times x cubed, and this thing goes on and on. And so we can plug these values in. This is 0. Then this is plus x plus 0 times x squared. And then from the previous page, you'll remember we got -2. So this is plus -2 over 6 x cubed. And then we didn't do any more terms. And so right away, what we get is we get x minus 1/3 x cubed plus dot, dot, dot. And you'll see that we did get the same first 2 terms that we got in a completely different manner. So if you go back 3 pages, look what the first 2 terms are, x minus 1/3. Now, if we kept taking derivatives, we would get 1/5, 1/7, etc. Clearly, though, the calculation involved in doing the Taylor series is overwhelming. I mean, the third derivative was a pain to get. Imagine if I have to keep getting more. So we see that the power series, the theory of power series, tell us that this is a much quicker way to obtain a series than what we did. All right. Now, good news is, even if you don't understand this piece or you're kind of overwhelmed by that in this, there's some good news. And that is there's a bunch of theory that gives us a lot of information for free. And so we're going to write that down on the next page. And if you have a question before we go there and do that, please let me know. Questions, comments?
Can you go to the table?
Just one back or
Yeah, one.
this
Just
page?
A simple question, right? So for example, that 1 plus x squared to the bracket squared.
Here?
Yeah.
Yeah,
So when you take it up, only the outside 2 becomes a minus, right? Not the inside.
that's correct. Yeah.
So if it was open, so it would be also.
Well, if this were no parentheses, I couldn't flip it up the way you want to do it.
Well, there is a plus between, right?
Right, right. If this were just 1 plus x squared,
Yeah.
when you take it upstairs, notice what I did here. The whole denominator is net minus 1. Okay, so here's where we're at. Here's what's an amazing fact. And we're just going to take it for granted. I don't want to call amazing formulas. Let's say amazing formulas we get from the theory of power series, and hence Taylor series. So for example, we get that e to the x is equal to its Taylor series. It's equal to it. And it's, what is its Taylor series? It's 1 plus x plus 1/2 x squared plus 1 over 6x cubed. By the way, the general formula for this is 1 over n factorial times x to the n. We get this as true. And what's amazing is this is true for all x. E to the x is equal to that for all x. Same with sine and cosine. We get the sine of x is equal to x minus 1 over 3 factorial x cubed plus 1 over 5 factorial x to the 5th minus 1 over 7 factorial x to the 7th. We get this for all x. Cosine is very similar to sine. It's all the even powers. That is true for all x. Now, we also found a couple more. We got, for example, the arctan. What did we find that to be? That was x minus 1/3 x cubed plus 1/5 x to the 5. Notice there's not factorial on these ones. Now, where does this converge? Now, this one is not for all x. Well, it actually, here, it will converge for 1. So, by the way, did we have that one? Is that the one we had? Yeah, arctan. it makes it look like it should converge for -1 and 1. So where does the arctan converge? Well, again, as I suggested, we can't say, we can't, I shouldn't say we can't. We probably could, but there's too much sort of theory involved. That we don't usually cover it in calculus 2. But let me reiterate sort of what I was saying is, if you look at this series down here, if you replace x with 1, the series will converge by the alternating series test. But that doesn't mean it's going to converge to the arctan of x. Turns out it does. But what about for -1? Well, if you plug -1 in, it's going to converge as well. For the same reason. Question is, does it converge to the arctan of -1? Oh, I'm asking you. What do you think?
And what is the sign change? What is the minus of the plus?
What do you mean they change? Oh, you mean, but okay, again, think about what I'm saying here. Clearly it's going to converge if x is -1 or 1, but that doesn't, what we're saying is, not only does it converge, but it has to equal the angle or the arctan of that.
So I don't think it's still equal, right? When you do -1, right? So the sign change, will it still equal to after that?
Well, yeah, because, okay, so, okay, good. Okay, I see what you're saying, alternating. So, right, when you plug 1 in, it alternates. When you plug -1 in, you get negative, positive, negative, positive.
So does that equal to after that?
Say that again.
Does that equal to after?
That's the point. That's the question we'd have to ask.
I think it doesn't.
What makes you think it doesn't?
For the sign split, right? So it becomes
Well, what does that mean?
there's a slight change between the.
Well, but what makes you think that doesn't mean it can't converge to it then? Just because the signs change doesn't mean. I mean, the inverse tangent of -1, go to the graph, it's a negative number. So
When you plug -1, you also find the inverse of after.
no. Again, you're missing with the question. So let me reiterate this because I don't think it's clear. I'm not arguing that this converges for -1 and 1. What I'm arguing or asking you to ponder more is a better way of saying it, is what makes you think that it actually, the number you get in the series sum is the same as the arctan at that number. We get it for free if x is between -1 and 1. We don't get it for free. We have to do work when they're not between -1. Now, I told you that the theory tells us it is gonna, this equation holds for 1. Now, what I was trying to get you to think about is, do you think it holds for negative 1? But then, okay, so you say no, but why?
I think
Why though? What makes you think? What's the difference?
my answer is like the same, right? So when you put one,
Okay, yeah. So if you put 1 in, you have 1 minus a third plus a fifth minus a seventh.
so you get a positive number.
Right. Okay. And if you put negative 1 in, you'd have negative 1 plus a third minus a fifth. But that would be a negative number. But I'm telling you that the arctan of negative 1 is negative. Go back to
So yeah,
the graph. What's the arctan of negative 1? You could clearly see it's a negative number. Is that the same number that the series sums to, is my question. And what I'm trying to get you to think about is the symmetry here.
I think
That's sort of what I'd like you to sort of ponder.
so you mean on top, okay, I get what you mean. So it will, right?
Well, I mean, that you would think because of symmetry that would be the case. Doesn't necessarily mean it is.
What if you use the radius thing?
If I use what?
The radius,
The radius of conversion?
yeah.
Yeah, but that doesn't help us with the endpoints. The only thing we get, the only thing we get from the power series theory, with the radius or the interval convergence, is just inside. Nonetheless, it does converge. I mean, I've already written it down. It does converge for negative 1 less than or equal to x less than or equal to 1. And by the way, we did have one more, and since we're out of time, we should still write it down. We did have, how did I what?
Come to the conclusion that it does converge. Apart from, you also saw the symmetry, or you had another?
No. I'm telling you, the alternating series test tells you it converges at 1 and negative. And I'm telling you, using advanced theory that you would maybe learn in a higher course, you can show that it not only does it converge, but it equals. That's what I'm saying. So these ones are equal for all x. And then we had one more. The last one we had was this guy. We're out of time, but we'll probably use it. But this creature right here, the natural log one. This one will converge. It turns out this will converge at negative 1, but it doesn't even make sense at 1. Clearly, it's not going to matter at 1. And this, when you plug x equals 1 in, this is undefined. So, anyhow, that's that. And we'll talk more about this stuff tomorrow, but you now have the necessary machinery to answer all the homework questions. So please bring questions tomorrow, and hopefully I'll see you tomorrow. Thank you guys very much. Have a good one. Take care.
So when you, let's say